Hello and welcome to, we're continuing, let me move my mic. Hello. Okay. The IB Chemistry May 2025 exam walkthrough for TZ2. In this video, we're going to be going over question 1 for section 1B for the SL version. However, the HL version is also the same for question 1 at least. And so two pieces of advice before we even get into the exam about paper 1B. Paper 1B, if you have not already looked at the tools section of the subject guide, you need to. That is where everything you need to know is, okay? It's very helpful. The Oxford book has a big yellow section in the middle of the book that goes into the tools section. Also very helpful. 10 out of 10 would recommend. Paper 1B is kind of like the IA in test form. Okay, that's my hot take. And so another thing that is also helpful is the subject reports from the IA, if that makes sense. Because a lot of the things that they bang on students for, I don't know a better word than harp on students for, all the things that they kind of get mad at students for doing, those things are echoed in the mark schemes, if that makes sense. And so the biggest example of that is actually this first subpart, okay? And so immediately this question is, we have this titration that's going on, is we are measuring the amount of calcium ions using this EDTA type of titration. And we're making a standard solution of calcium chloride in order to do it. And so the first question is, state the most appropriate glassware to make 250 centimeters cubed of a calcium 2+ solution. Okay. And so this is one where literally every year in the subject report for the IA, the moderators get mad at students because they say students should be using volumetric glassware for every single, like, making a solution. Is if you're making a solution, you should not be using an Erlenmeyer flask. You should not be using a graduated cylinder. You should not be using a beaker. You should be using a volumetric flask. And they get mad about this every year. And this is echoed in the mark scheme, because the mark scheme is, it's a volumetric flask, specifically a 250, but you don't have to say the size. And so that also brings me to my next piece of advice about paper 1B is I would put as much as possible, every little detail. As long as you're not saying something that's incorrect, you're not going to be punished for it. If you contradict yourself, that's another story. Okay, paper 2, I tend to say not to do this because it's more predictable, but paper 1B, it's so new, it's unpredictable. And so if you put more stuff, and as long as it's all right, you're more likely to hit the stuff on the mark scheme. If you're someone who tends to say stuff that's wrong, maybe don't do this. But anyway, so that part 1 is staying the most appropriate glassware. That would be that volumetric flask. Volumetric flask. And I actually, I stated this in previous videos, I took this exam myself under simulated time conditions. And so, like, whenever I say put extra details, that's not me saying, oh, I don't know your time management. No, like, you have time to do that. I swear, because I did it. And so I also, whenever I did this, is I was checking my own work, and I was like, just to be safe, I'm going to put 250 centimeters cubed. Just to be safe, let's put that extra detail. The mark scheme was just the volumetric flask. For part 2, for this part A, is describe the steps involved in preparing a standard solution by dilution of the initial calcium chloride solution. Okay, and so this is, once again, in tools, dilution. Ooh, crazy. And so this is one where there was a lot of options for the mark scheme. It was just any two. And so this is one where there's so many lines. Once again, it's just put anything you can think of. And so the exact thing that I actually put, this is exactly what I put when I took this myself, is I put calculate the volume of the initial solution via C1B1 is equal to C2V2. And then, so that would be the first kind of step. And then you would add or transfer the first volume that you just calculated to the volumetric flask. And then just to be extra, I said with a volumetric pipette. I'm going to be honest, not a lot of schools have these because they're expensive, but in this hypothetical scenario, we do pipettes. And then fill to the line. This is the detail a lot of students miss, is that whenever you're using the volumetric flask, there's that little line that you're always filling to. So fill to the line with DI water in the flask. And then the last step was then either invert or shake until combined. And so even then, that still didn't fill in all the lines. And so, like, whenever you're answering this, it's literally you should imagine that you are in the lab doing this yourself in every little detail of the steps that you would take. As long as they're all right, once again, you're more likely to hit the mark game because this one was literally any two and it was just a list. Okay. As long as you're not saying something that's wrong, then you're good. Okay. And so, like, this is literally as if I'm visualizing myself in the lab, as these would be the steps that I would take. Or if I was describing to another student how you would do this is you want to always, like, whenever you're doing the lab procedures, you always want to hit those little details, right? You want to assume that the examiner is a dumb baby who knows nothing. So you want to say all the little details. Don't say, oh, well, they know that. Like, they know you filled to the line. No, assume they know nothing. Say everything. Okay. So that was that number 2. And it was any two. But I'll put a screenshot of the mark scheme there. But yeah. B was calcium chloride is not used to make it because it absorbs water. And so describing how you could remove all of the absorbed water. This is one where they actually did both of this and the standard solution. They did both of these in different shapes in all of the time zones, actually. I looked at 1 and 2 as well as 3. And so with that one, whenever you are essentially trying to remove water, is there's 2 options. Is that you could either essentially like dry it in an oven or just like heat it up, essentially. And then the biggest thing is that you would then need to weigh it until it is a constant match. Because if you don't weigh it until a constant mass, there's no way for you to know that all of the water has been absorbed. Okay. And then this was one where actually the mark scheme was interesting, where it said heat to constant mass slash same mass twice. So this heating it up and constant mass thing were both combined into one mark essentially. And then mark 2, this was one I actually missed when I took it, was cool slash store solid in a desiccator slash vacuum. So then store and desiccator and or vacuum. I think vacuum is really unrealistic for students to get at the high school level because you all have never really worked with a vacuum very much. Desiccators are more common. But either way, so that was mark number 2 for that one, actually, is it is 2 marks. Okay. And so this is one where I feel like this gives kind of keys for future exams, is that whenever it is talking about like removing something, there is a chance, especially if it is 2 marks and you're not, and you can't, and it seems like, oh, what I put here is 1 mark. I don't know what that other mark may be. Is that you should consider the subsequent storage of whatever it is that you're doing, especially if it is something that absorbs stuff from the air. Because then it's like, well, how will you prevent it from then absorbing more stuff from the air? So if you remove it and then it just absorbs it back, that's not really good. So that is kind of a nice thing that we can now consider for future questions for future exams, since this is now precedent that has been set in this mark scheme. Okay, and so moving on to this part C of this question 1 is we're talking about how we have a sample of tap water that we are titrating against this EDTA. I assume we were trying to figure out if there was any calcium ions in there. We have this data that we are given, and the first part is suggesting 2 reasons why the volume added in trial 1 is much larger than the other values. And there's 2 marks for the 2 reasons. And so this is one where there's going to be many options. And so it's another one where, once again, you need to visualize yourself doing the experiment. Okay. And so, and specifically the experiment that's being done, not just generally. Okay. And so, like, the 2 reasons, 2 marks, and we have this data. And if you look at the data, you have your kind of trial 1, trial 2, you have 4 trials. Your first one, you have 26.15 volume that was needed of this EDTA that you were adding. Meanwhile, with 2, 3, and 4, it was around 24 and very close together. And so whenever you are doing a titration, there's a few steps that you need to do before. And since it didn't say that we did this explicitly, we can assume that we didn't. If it said it in the instructions that they did it, you can assume that they did it, obviously. But if it's not in the background information, you can assume they probably didn't do these steps. And so this is one where, once again, I'm going to put actually my exact answers because these were the ones that I came up with and these were on the March scheme, so they worked. And so the one that I put was when you're doing the titration for the first time, yes, this is a lot of words. When you are doing a titration for the first time, it's very common to have a rough uh, go at it, if that makes sense. You're really unsure about the endpoint at first, so you do it really quickly, just so that it doesn't take a lot of time to see a rough guesstimate of where the endpoint's going to be. The endpoint can easily be overshot. That's what, like, over titrated. After trial one, you then know where to slow down and you can be more accurate. You know where to slow down and can be more accurate. Okay, so that was the first option I did. Whenever I was imagining myself doing a titration, that's a very common reason why that trial one tends to suck. Trial one always does tend to suck, and that is why. Meanwhile, for part two, I put a star by this, and I was thinking where I was like, maybe, and I put another thing that you do, and now remembering the own labs that I have my students do is one of the part of the procedure is rinsing the burette with whatever your titrant is that you're adding, because otherwise it may have a little bit of water in it, and then that would be a systematic error because your concentrations would be consistently lower. Okay, and so I put maybe the burette wasn't rinsed with EDTA. And so whenever you do this, that means that essentially the EDTA would have been more dilute because it would have been combined with more water than expected. Trial 2 wouldn't have this problem because then trial 1 would be acting as that rinse. So that's what I put for that one. And so I also put another, I always like to, especially for this one, because the Mark scheme has many options. I'm putting screenshots, it's right there. And so our options were essentially that it could be that once again, that titration was done quickly on purpose to really get an estimate. That it was not rinsed with EDTA or that it was contaminated. So both of my options were correct. The other things you could have said were that the liquid at the end of the burette tip, like normally your initial readings, what's the word? Normally for your initial readings is you remove the bubbles. Okay. And so this option is essentially saying that you did not do that step and therefore you essentially had some stuff at the tip. And so whenever you were adding stuff, that added like an extra milliliter. That was an option. Another option was that it was leaking or just wasn't shut correctly. And so, or that you had added some extra titrant in order to confirm that the color change was complete. All of these are very good options. And so once again, these are all very much so you have to visualize yourself in the lab. If you've done a lab similar to this, should have done a titration you're at some point in your career. And so that imagine that because imagine those steps. This part 2 is stating the name that is given to a value that differs significantly from the others. This would be that trial 1. It's an outlier. That's it. Because And that's a big thing in your IA. They want you to look at outliers. So once again, this is why I'm saying it's like an IA in test form. Other things they accepted mistake. I thought that was funny. They also accepted anomaly, anomalous value. I don't know if I'm pronouncing that right. Not concordant or rogue value. That sounds like a villain name. Like you're a Batman supervillain. Rogue value. So they accepted all of those. So that would be that one. Okay, so this is the part 3 of part C. Okay, and so this one is, I'm not gonna lie, this one stumped me. This, like I've said, paper 1B is, this mark scheme is very unpredictable. There's not a lot of patterns yet for future exams. And so we're trying to analyze this in order to figure out how to approach future exams for greater success. And so this one says, suggest a reason why trial 1 should not be included when finding the mean volume of EDTA used. Okay, so this is one where it stumped me at the time. And so now I've kind of thought about kind of how you should kind of think about this. And so the way you should think about this one is, like I've said, paper 1B is kind of like the IA and test. Okay, and so you're kind of thinking about why students, what are the best justification for outliers in an actual IA is what those examiners like to see. And you can kind of see those like in the subject reports and their comments and reading other IAs as well as your own. Okay. And so this is one where whenever you kind of have an outlier is usually the reason why that is justified in your report. It's usually you're like, oh, here's a graph with the outlier. Here's a graph without the outlier. The line of best fit fits better. Or something along the lines of like, oh, well, here's the, like, you have your measured dependent variable, but then you have your calculated dependent variable. So in this case, our measured dependent variable would be the volume of EDTA used, but our calculated would be the concentration of Ca2+ ions. And so usually whenever you kind of have an outlier, it's because then your calculated thing would be off. Okay. And so like one of the accepted answers here would be because, oh crap, because the average concentration, actually we'll just go brackets, concentration of Ca plus ions would be too high. That was an option that you could have put. Another thing that they did accept was also simply calculating the average with and without to show that the average would be too high. So in this case, you would go back, you'd go, oh, this with, where's my calculator? Seriously, where did I put my calculator? Here, I'm dumb. Okay, so with, it would be a 26.15 plus 24.25 plus 24.3 plus 24.2 divided by 4. And so we'll say average width would be 24.73. And then without would be 24.25 plus 24.30 plus 24.20 divided by, hello? Oh, okay. Okay, divided by 3 would be, without, would be 24.25. So that was another option that you could do literally what they were asking you to do, both with and without, to then kind of justify it. So then you could say, oh, that would be too high. Okay. Other things you could have done was referencing the uncertainty, concordant values. I'll put the mark scheme here. There were lots of options. And a lot of them are essentially with references to precision, as well as the kind of subsequent calculations that are affected by the mean volume of EDTA used, if that makes any sense. And so, once again, whenever we, in the future, if we are asked about outliers, those are the kinds of things that they are looking for, regardless of what the experiment is. Those are the kind of things you should be considering, precision, and the calculations that are done with those values. Okay? And then our IV 4 would be calculate the percentage uncertainty and the volume of EDTA used in trial 2. This is one, they do this all the time. They do this all the time with the burette. Is the burette, they do it all the time. So you have It's for the final volume. And a lot of you all want to do this, keeping this 0.05. No. No. Okay. Is this volume added is the final minus the initial. Okay. And so whenever you subtract two values from each other, you add their absolute uncertainties. So the absolute uncertainty for the volume added would be 0.1 plus or minus 0.1. So it's 0.05 plus 0.05. Okay. And so your percentage uncertainty is your absolute divided by your value times 100. So this is going to be 0.1 divided by the volume of EDTA used in trial 2 would be 24.25. 24.25 times 100. Okay. And I can't do math in my head, so I'm doing that in my calculator. 0.1 divided by 24.25 times 100. So that would be 0.41% as your absolute uncertainty for that one. Okay. They also accepted 0.4 for fungies, I guess. I'm not going to lie. With the sig figs, it does get very unclear what they accept and what they don't accept. What I would give to mark an exam as a official IB examiner, because I would love to know what they accept and how the leniency works. But anyways, I'm getting off track. So that would be this part 4. And finally, we have this last part D, where we have a stock solution of calcium chloride being diluted to now make some new solutions of known concentrations. We're using spectroscopy. No, spectrophotometry. God, those two are two different things. Spectrophotometry to then essentially get the absorbance of these solutions and therefore their concentration. And so the first bit is to essentially determine the concentration of calcium ions in a sample of tap water with an absorbance of 0.09. Okay, and so the way that you can do this is first you just need to draw a line of best fit for your calibration curve. This isn't, which is also the part 1 that I ignored. Oops. So we're gonna draw a line of best fit. You just need to draw a straight line with a ruler. I don't know why, but I don't think it was this time zone's mark scheme. A different time zone's mark scheme was oddly specific about the fact that these lines of best fit need to be with a ruler. If it looked like it wasn't, to mark them down. I don't know. Bring a ruler on exam day for paper 1B. Anyways, so they need to have an equal amount of points either above or below the curve. And so I'm just kind of going, yeah, eyeballing it at first. Okay. We've got 1 above, 3 below. This is hard. Go there. No, let's. I'm thinking. That gross. Nope. Listen. Okay. I see. Okay, so that has 2 above, 2 below, roughly. And we're going to extend this that way, and then let's add this on that way. I don't have a ruler, so this is essentially the closest that I have. Okay, that looks decent to me. So we're going to go with that. If I had an actual ruler, I would have gone across the whole thing, but I don't have an actual ruler. Oh, there's a ruler function on GoodNotes. Hold up. Wait. Listen. Wait. Okay. How do I do this? I'm going to go. It's like 1 above, 1 below, 1 directly in line. Okay. Now can I just go? Oh, that's cute. Okay, so now I have my ruler done. So that's our line of best fit. So you have a 3 that are kind of exactly 1 little bit below, probably a little outlier. I don't know, feels right. Okay, we're going with that. Once again, I don't know how strict they are whenever they're marking these. Anyways, so our part 2 is then determine the concentration for 0.09. So we're just going to go to our absorbance, not our concentration. Don't do what I did. Our concentration, our absorbance, into 0.9, which is in between 0.8 and 0.10. So for some reason, these aren't evenly spaced. So 1, 2, it's like roughly There, we're going to use our ruler again to simulate being on the actual exam. So that would be kind of, is this exactly angle 180? Okay, that's funky fresh. Anyways, I need to move it. Position. No, I don't want to set it like that. I just want to move it. Oh, I do it this way. Okay. So we're going to go in between. Boo. That feels right. Okay, so that would be 0.09. And we're going to mark it there. Okay, cool. Get rid of the ruler. Cool. That's our point. Bam. So that would have a concentration of literally just 9 ppm. Okay, the official mark scheme says 9.2, I think. Yeah, 9.2, but it says it can be based off of the line of best fit. Does that mean they would then mark off your line of best fit? I don't know. Great question. These are the insights that I don't know. I look every day to apply for a position, but unfortunately, they're not hiring. So, okay. Anyways, 9 ppm. We're going to go with that and assume that they would mark it right. If you get 9.2 based on your line of best fit slit, this part 3, finally, last part of this question 1, is the 4 ppm solutions were made by diluting 2 centimeters cubed of the stock solution to 25 centimeters cubed, and to calculate the concentration of the stock solution. That's going to be C1, V1, C2, V2. Oh my god. Okay, so C1, oh my god, V1, C2, V2. So we're calculating C2. Our C1 is our 4 ppm. Ignore that little glitch in the video. My screen randomly stopped sharing. Anyways, I also realized that I had put 4 ppm as C1. The 4 ppm stock solution, not stock solution, the 4 ppm solution was made. That means it's the C2. Ooh, so we're solving for C1 actually. So C1, we took 2 centimeters from this unknown solution, and now we have 4 ppm and 25 centimeters of it. Okay, so we're just going to do 25 times 4 divided by 2. And so that's going to give us 50 ppm, which is the correct answer here. And that one is question 1. Yippee!